determination of fugacity. This is the second method actually. Determination of fugacity using compressibility factor Z. Compressibility factor. Compressibility factor. How to determine fugacity using compressibility factor. Okay, see, we know very well alpha is equal to, yesterday we discussed this, RT by P. This is the molar volume for ideal gas minus molar volume of the real gas. Okay, we know this equation. Right, now what I am going to do is that, you know very well, compressibility factor, what is this? PVM by RT for 1 mole of gas. Okay, you take any gas, the gas may be real or ideal, but here we are going to determine fugacity for real gas. So for real gas, you find out, you take 1 mole of real gas and find out P into Vm, okay, pressure into volume of the gas, multiply these two and divide this by RT. That quantity is what we call as compressibility factor. And you know very well, compressibility factor for ideal gas, let me write here. For ideal gas, PV for 1 mole, PVM by RT is equal to 1. So for ideal gas, compressibility factor equal to 1. Remember this, very important. For ideal gas, compressibility factor is 1. For real gas, okay, the value may be greater than 1 or lesser than 1 depending upon whether attraction exists between molecule or repulsion. Okay. Now what I am going to do, I am going to make some rearrangement here. Okay, so chinna rearrangement panna poren and I am going to get an expression for compressibility factor here. How to do that? Okay, very simple. Multiply throughout by P and divide throughout by RT. Very simple. See what I am doing? Multiply throughout by P and divide throughout by RT. So what we get is multiply alpha. In the left hand side we have alpha, so multiply with the P. So alpha into P and divide by RT equal to here. If I multiply with the P, I have P in the denominator here. So this P and this P cancel. RT cancel. So we will get 1 here. Minus, if I multiply here, I will get PVM by RT. Now see this. What is PVM by RT? PVM by RT is nothing but compressibility factor. Correct? So alpha into P by RT equal to 1 minus compressibility factor. Okay, see in the above equations, let me take this equation as A. The equation I have alpha here. Okay, now I am going to write this alpha in terms of compressibility factors. What is alpha? Alpha is equal to 1 minus Z compressibility factor by divided by P. This P will come here and RT will go to the numerator. So this is the alpha in terms of compressibility factor. Substitute this value in the place of alpha here. So equation A becomes ln F over P equal to minus 1 by RT is there already, into, in the place of alpha I am going to put this value. Anyway RT is constant, so you just take it out. RT is constant, take it out, and integral 0 to P. Okay, then write this one, 1 minus Z by P into dP. Okay, this RT cancel each other, and here you have minus sign, so multiply this by minus, so you will get minus 1 plus Z. So just change it into Z minus 1 by P. Let me write in the next page, just copy down. Therefore we can write ln F by P as multiply the minus inside the integration, so we get integral 0 to P. Now 1 minus Z become Z minus 1 by P into dP. So this is another equation by which you can find out fugacity. Remember, compressibility factor Z is an experimental quantity. We can measure experimental quantity. you can measure experimentally. Okay, you can measure Z experimentally for various pressures, right? So since this is experimental quantity, for various pressure values you calculate compressibility factor and subtract 1 from that, okay, and draw a plot. See how to find this integral. How to find this integral is very simple. What to do? Find out Z value, compressibility factor value for various pressures, and subtract 1 from that, subtract 1 and divided by pressure of the gas. Plot this quantity versus P. Okay, I am just plotting this in the y-axis, Z minus 1 by P in y-axis, and this pressure in x-axis. If you plot, you will get a graph something look like this. Now, at what pressure you want the fugacity? You எந்த pressure உங்களுக்கு fugacity வேணும்? Okay, suppose I want fugacity at this pressure P, then draw a straight line here and find out the area under this curve. This area is equal to the integral 0 to P compressibility factor Z minus 1 by P, okay, into dP. You will get this integral, or you will get this integral by finding the area. Okay, up to some pressure P. If you want some other pressure, then take the area under the curve up to that pressure and substitute that value here. So this you can find by finding the area of this curve, area under the curve, substitute that area here, which is equal to ln F by P. Okay, yes, take two. Observe this carefully. Suppose alpha, residual volume alpha, okay, alpha is constant, right? Suppose alpha is a constant over a range of pressure. Okay, ஒரு certain pressure வரைக்கும் alpha constant னு வெச்சுக்கோங்களேன். Suppose actually நம்ம last class பார்த்தோம் alpha varies with the pressure. நாங்கள் சொன்னேன் உங்களுக்கு கவனிங்க. Alpha என்ன ஆகுது பாருங்க, alpha versus P. Last class we discussed it, right? As you increase pressure, alpha changing. See, alpha decreasing. Alpha changes with the pressure. But நான் இப்போ என்ன சொல்கிறேன், suppose alpha is a constant over certain pressure. Okay, in that case, right, in that case, listen, this equation ln F by P equal to minus 1 by RT. We derived this equation before. Integral 0 to P. We write alpha into dP here, but now alpha is a constant up to some pressure. See, I am taking some pressure up to this pressure. Let us assume that alpha is independent or constant. Alpha into dP. Okay, we can write like this. Now see this, integral of dP is P, upper limit is P, lower limit is 0, therefore you will get P. So we get minus alpha into P by RT. This is ln F by P, or I can write F is equal to, fugacity F is equal to, one second, paper parakadu, yeah. So fugacity F is equal to, if you remove the log, what we get is F by P equal to e power minus alpha into P by RT. We get this. Then what is F? F is equal to P into e power minus alpha into P by RT. Take note. This is the equation for fugacity if alpha is constant up to the pressure P. Right? Take note. This is another expression available for the determination of fugacity. And suppose we will take some real gas. If that real gas follow this equation, P into, okay, molar volume of the gas minus B into RT. Okay, this is an equation of state for a real gas, for 1 mole of real gas. Okay, I have taken 1 mole of some real gas. That real gas follow this equation. Okay, if it follow this equation, what will be the fugacity of that gas? Right? This is also an important question in many competitive examinations. Take note. Right? People ask this question in competitive examinations. Right? Suppose if an equation follow this equation, right? Then how to find the fugacity? Okay, so we can find the value of this. How to do that? Listen, how to do that? It's very simple. Multiply this by P, so you'll get PVM minus PB equal to RT. Observe carefully. I just multiplied with the pressure. Vm is the molar volume, right? And you can also write like this. See, PVM equal to RT plus PB. Bring this PB to the right hand side, and now divide throughout by RT. Divide throughout by RT. We get PVM by RT, okay, equal to 1 plus PB by RT. I am dividing throughout by RT. So we will get 1 plus PB by RT. Okay. What is this quantity? Can anyone tell me what is this quantity? PVM by RT?
Z, sir. Compressibility factor.
Very good. Compressibility factor equal to 1 plus B into P. Instead of PB, I am writing B into P by RT. Bring this plus 1 to the left hand side. So compressibility factor minus 1 equal to BP by RT. Okay, and bring this pressure also to the left hand side. So compressibility factor minus 1 by P, right, is equal to B by RT. Here B is a van der Waals constant, R gas constant, and you know very well in fugacity measurement we are changing only the pressure. Temperature remains constant. So all these quantities are constant now. Okay, now see, you know this fugacity equation. Just now we discussed ln F by P, ln F by P equal to integral 0 to P compressibility factor Z minus 1 by P into dP. Do you remember this equation? Just now we wrote. Right, this is fugacity in terms of compressibility factor. Just now we derived this. Now see, I got this quantity for some gas which is obeying this equation. Okay, I have some real gas, 1 mole of some real gas. That gas obey this equation of state. Right? If it obeys this equation of state, then what will be the fugacity expression? So in the place of Z minus 1 by P, I am going to put this value. Anyway, B by RT is a constant, so you can keep it out. So ln F over P equal to B by RT. Integral dP is P. Upper limit is P, lower limit is 0, so you will get only P. Right? Now, this is logarithm of F by P. Okay, then what is F by P? You take the exponential, so e power BP by RT will get like this. Or F is equal to pressure into e power BP by RT. Yes, this is the expression, okay, we used to calculate fugacity of a real gas which follow this equation. Okay, take them. Sometimes people ask questions like this. Take them. Is this clear?
Yes.
Okay, take it. This is actually very simple one, but you require some prior idea, that's all. Yeah, so we have discussed.
B nana, sir.
Okay, listen. Suppose you take some extensive property, right? Some extensive property, say for example X. X is an extensive property, right? And you consider a open system. First you take some property X, which is an extensive property, and take an open system. Since system is open system, molecules can go out, new molecules may come in. Okay, so it's an open system, and also assume that system contain many components, multi-component. Listen. So we are going to discuss the next important topic called partial molar properties. You take some extensive property X. I have told you this extensive property. It means it may be internal energy or enthalpy or Gibbs free energy, whatever it is. It should be an extensive property, right? Now you take an open system containing multi components, many components. In that case, the extensive property X is a function of temperature, pressure, number of moles of component 1, number of moles of component 2, number of moles of component 3, etc., etc. Okay. Now observe this carefully. If there is any change in X, the change occur either due to change in temperature, or change due to pressure, or change due to number of moles of component 1 or number of moles of component 2. Okay, so how changes occur? The change in X may occur due to change in temperature at constant pressure and at constant number of moles of all component, okay, J, right, into dt, plus the change occurs due to change in pressure at constant temperature and number of moles of all the component, number of moles of all the components should be constant, into dp, then plus change in X due to change in number of moles of component 1. Yes, sometimes the component 1 may go out, therefore number of moles of component 1 may change, right? So due to the change in number of moles of component 1, the change occur in X into dN1, keeping temperature, pressure, number of moles of temperature constant, pressure constant, number of moles of all the component constant except component 1, because 1 alone varying, right? Similarly we can write change in extensive property X divided by change in number of moles of component 2 into dN2, keeping temperature, pressure, number of moles of all the component constant except 2. Like that we have many terms. Okay, I'll explain again. See, the topic now we have chosen is partial molar properties, right? For partial molar property we should take some extensive property, right? It can be Gibbs free energy or internal energy or Helmholtz free energy, whatever may be, some extensive property. Even it can be volume, right? Volume also extensive property. Right, now you take a open system containing multi components. Okay, I have components 1, 2, 3, 4, etc. And the system has some temperature T and some pressure P. Okay, now the extensive property X for the system depends on temperature of the system, pressure of the system, number of moles of component 1, number of moles of component 2, number of moles of component 3, etc. Okay, now the change in X, okay, the X changes due to change in temperature or change in pressure or change in number of moles of component 1, right? So what is the change of X due to temperature? Yes, this term gives you change in X due to change in temperature. The second term gives you change in X due to change in pressure. Third term gives you change in X due to change in number of moles of component 1. And this term will give you change in X due to change in number of moles of component 2. Like that we have many terms, plus etc., etc. Okay, right? Take note. This quantity here, dou X by dou N1, keeping temperature constant, pressure constant and number of moles of all the component constant except 1. This quantity is nothing but partial molar property. We put the symbol X bar. Okay, it is nothing but partial molar property for the component 1. This is the partial molar property of the component 1. Right? Similarly, what is the partial molar property X for the component 2? Partial molar property of the property X for the component 2. How to write? Dou X by dou N2. You should keep temperature, pressure, number of moles of all the component constant except 2. Okay? Observe this carefully. Yeah, observe this carefully.
Sir.
Listen, now I am going to take a specific extensive property, say G. Gibbs free energy. Right? And you know very well, Gibbs free energy for an open system containing multi-components, right, is a function of temperature, pressure, as I said before, number of moles of component 1, number of moles of component 2, etc. etc. Now, the change in Gibbs free energy occurs either due to change in temperature or pressure or, okay, so I can write dou G by dou T, change in free energy due to change in temperature, keeping pressure and number of moles of all the component constant into dt plus dou G by dou P, change in free energy with respect to pressure, keeping temperature and number of moles of all component constant into dP plus change in Gibbs free energy due to change in number of moles of component 1, keeping temperature constant, pressure constant, number of moles of all the component constant except to 1 into dN1, right, plus dou G by dou N2 at constant temperature, pressure, number of moles of all the component constant except 2 into dN2 plus etc. etc. It goes like that. Okay, take note. See, I am writing the same expression for the extensive property G now. Gibbs free energy is an extensive property. Okay, before I wrote some general property X. Now I took a specific extensive property G. Okay. Now listen. Here dG is equal to, observe this carefully, we already discussed, dou G by dou T at constant pressure. Dou G by dou T at constant pressure is nothing but minus of entropy into dt plus dou G by dou P at constant temperature is nothing but V into dP. Okay, take note. Plus, listen, this quantity dou G by dou N1, keeping temperature, pressure constant and number of moles of all the component constant, this is nothing but molar, partial molar Gibbs free energy. Yes, partial molar Gibbs free energy, which we write normally as G bar. For G1 bar. G1 bar is nothing but partial molar Gibbs free energy, which is nothing but chemical potential. Yes, you are right. G1 into dN1 plus G2 bar into dN2 plus etc. etc. This G1 bar, or in general, okay, G1 bar is nothing but mu1. This G2 bar is nothing but mu2. What is mu1? Mu1 is nothing but chemical potential of component 1 in the mixture. It is not a pure substance. Observe carefully. What is mu? Now, listen, instead of writing mu1, mu2, mu3, etc., I'll write directly or generally for some ith component, right? Chemical potential for ith component equal to dou G by dou Ni, keeping temperature constant, pressure constant, and number of moles of all the component constant except to I. Take note this. Is this clear? I repeat. Listen. So G1 is nothing but molar Gibbs free energy, partial molar Gibbs free energy of component 1, partial molar Gibbs free energy of component 2, right? We have many terms. Partial molar Gibbs free energy of component 1 is nothing but chemical potential of component 1. Similarly, G2 bar is nothing but mu2. So what is mu I in general? Mu I is equal to dou G by, okay, dou Ni. I am just writing general expression. keeping temperature, pressure constant, number of moles of all the component constant except the ith component, ith. And this is what we call as chemical potential of ith component in terms of Gibbs free energy. Okay, take note. So that this equation becomes minus SDT plus VDP. Instead of G1 bar, I'll put mu1. So mu1 into dN1, and instead of G2 bar, I'll put mu2 into dN2 plus etc. etc. Or I can see this term, we have so many terms here. So in short, okay, we can write, or shortly we can write summation mu I into dNi. Okay, take note. We have already discussed this. See, you may be remembering this, right? Listen, these four equations of thermodynamics: du, dh, dg, dA. Let me rewrite. Just observe this. du is equal to TdS minus PdV. dH is equal to TdS plus VdP. dG is equal to VdP minus SDT.
Minus SDT.
Yes, minus SDT minus PdV.
PD.
Okay, all these four equations are applicable for
It's a closed
For
system.
closed system and
Very good.
for
Pure system,
system.
right? Now I'm having open system. With many components. So listen, just now we discussed Gibbs free energy. You'll get an additional term. See this, VDP minus SDT is there. See, just check it. We have VDP, we have minus SDT. These two are there, and we have an additional term. So in DG, I'm giving you an additional term, which is summation mu I into dNi. Okay, similarly add that additional term for other extensive properties, right? Mu I into dNi. Here also summation mu I into dNi. Here also you add summation mu I into dNi. Now these are four fundamental equations which is applicable for open system. Open system containing many components. Okay, take note. See what I'm going to do now. I'm going to write chemical potential in terms of internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy. How? See this. First I'll take this equation, du equation. Okay, so let me take this as equation number 1. So I'll take equation 1. In equation 1, listen, I'm going to keep entropy constant and volume constant. Observe carefully. At constant entropy and at constant volume. I'm keeping entropy constant and volume constant. If you keep entropy constant, this becomes 0. If you keep volume constant, this becomes 0. Then I can write du is equal to, right? I'll remove the summation. So we can write mu1 dn1 plus mu2 dn2, right? Plus etc. etc. And I have mu I dni in general, mu I dni. Okay, now I'm going to write general expression for chemical potential of some ith component. So what I'm going to do, I'm going to keep n1, n2, n3, all the component constant. Okay, so I'm keeping at constant number of moles of all the component n1, n2, l3 except the ith component. Except I am going to keep all the component constant. Therefore, dn1 becomes 0, dn2 becomes 0. So what we get is du is equal to mu I into dni. Bring this dni to the left hand side. So I can write dou u by dou ni, keeping entropy constant, volume constant, and number of moles of all the component constant except the ith component. This is nothing but the chemical potential of the ith component. Take note. This is chemical potential in terms of internal energy. Okay, take note. Okay, so we asked, see, we get this expression. Now I asked you whether mu I is a partial molar property or not. The answer is, okay, this is not a partial molar property. Why? Because the constants that we kept here is entropy, volume, and number of moles. If you keep temperature, pressure, number of moles constant, then only that property is partial molar property. So this property, okay, it gives you chemical potential, but this is not a partial molar property. Keep this in mind. Okay, take note. So in a similar manner, you take equation 2 and find out an expression for chemical potential for ith component, okay, in terms of enthalpy, right? You just proceed in a similar manner. I'll give you the final answer, but before that you try.
Dou H by dou N.
Let me write, just check it. See, from equation 2, I can write chemical potential of the ith component mu I is equal to dou H by dou Ni. Dou H by dou Ni, keeping entropy constant, pressure constant, and number of moles of all the component constant except the ith component. Okay, take two. So this is another expression for chemical potential of ith component in terms of enthalpy. Now I'll ask the same question: is this a partial molar property? Right. So this is also not a partial molar property. Why? Because we are not keeping temperature pressure constant, we are keeping entropy constant, pressure constant. Okay, so this set, if we keep as constant, it is not a partial molar property. For partial molar property, you should keep temperature, pressure, and number of moles of component constant. Keep this one. Okay, keep this in mind. Very, very important. Right, take. So now I'll write, so mu I is equal to dou G by dou Ni, keeping temperature constant, pressure constant, number of moles of all the component constant except to I. Okay, so this is this is chemical potential in terms of Gibbs free energy. Now the same question I'm going to ask: is this a partial molar property? Yes, this is a partial molar property because we are keeping temperature, pressure, number of moles constant. Okay, you are right. Now just try with equation number 4 and tell me the expression for chemical potential.
No,
No,
sir.
sir.
Yeah, this is an
No.
expression. See, this is chemical potential in terms of Helmholtz free energy, but this is not a partial molar property. This is not a partial molar property. Okay, take. Observe this. So we have discussed chemical potential, partial molar properties, right? Now as an extensive property and give some idea. I'll take volume. See, volume is an extensive property, you know very well. Pressure and temperature are not extensive. Pressure and temperature are intensive property. Volume is an extensive property. Okay, I'll take volume. Now listen, I'll take two components A and B. I'll take two components A and B which are present in open vessel. Okay, instead of 1, 2, 3, I have taken two components A and B. Right? So I have a component A, right, in one container. I have another component B in another container. Okay. Now, before mixing, what is the total volume of the two? Okay, before mixing. Before mixing, right, what is the total volume? See, total volume, I'll write just VT. VT means total volume. Total volume is equal to, before mixing, right, you find out number of moles of A and into what is the molar volume of A. Molar volume of A. Molar volume of the component A into number of moles of A plus number of moles of B into molar volume of B. If you multiply, you will get total. Okay, this is before mixing. After mixing, how to find the total volume? See, observe carefully. This is total volume after mixing. Okay, after mixing, see, you take the same number of moles of A. Now I am having a mixture. Okay, right, I am having both A and B as a mixture. In the mixture, what is the total volume? Total volume is equal to number of moles of A in the mixture into partial molar volume of A. Okay, let me write, just put A. So V bar A means it is partial molar volume of A plus number of moles of B into partial molar volume of B. Okay, take note. See, I have written total volume before mixing, total volume after mixing. Now I am writing total volume in general, total volume after mixing in general is equal to number of moles of the ith component into partial molar volume of the ith component. Okay, multiply this and add everything, you will get the total volume right after mixing. Similarly, total volume before mixing is equal to summation number of moles of each component and molar volume of each component. Okay, I took volume as an example and I am giving you this. Suppose if you take Gibbs free energy, yes, we can write in a similar equation. Gibbs free energy. What is the Gibbs free energy after mixing? Okay, write total Gibbs free energy after mixing equal to summation. We just write same Ni into partial molar Gibbs free energy, which is nothing but chemical potential.
Mu.
It's nothing but chemical potential, right? Take two. Here one thing is very important. You should keep. Take two. Yes. The next topic is the Gibbs-Deagon equation. Listen, we know very well for a open system containing many components. Okay, for an open system containing many components. Okay, we can write change in Gibbs free energy. I am writing the expression in terms of Gibbs free energy. You can take any extensive property, but this is the most important property in chemistry, so I am taking Gibbs free energy. So dG is equal to, this is VdP for open system, right? VdP minus SdT. If you write only this, it is closed system. For open system, you have the additional term. What is that? Summation mu I into d. Okay, I'll take this as equation number 1. This we know. We also know that Gibbs free energy, total Gibbs free energy after mixing, right? After mixing, total Gibbs free energy after mixing is equal to summation number of moles of each component into partial molar Gibbs free energy of ith component, which is nothing but chemical potential of the ith component. This also we know. I'll take this as equation number 2. Just now we discussed. Now I'll differentiate this dG equal to, okay, see, the change occur either due to the change in number of moles or due to change in mu I. So what I'm going to do, I'm going to differentiate this using UV method. So first keep number of Ni as such and differentiate mu. So you'll get d mu I plus, now summation, keep mu I as such and differentiate Ni. You'll get dNi. I'm using UV method. Okay, I'll take this as equation number 3. Now see equation 1 and 3. In equation 1 and 3, in the left hand side we have dG here. Here also we have dG. Okay, I'm going to equate these two or comparing these two. Okay, so comparing equations 1 and 3. Okay, so what I'm going to do is that in the place of dG, I'll put this one. Right, so what we get, summation Ni into d mu I plus summation mu I into dNi equal to, here we have VdP minus SdT plus summation mu I into dNi. Okay, now see this carefully. Here I have mu I into dNi plus mu I into dNi, right? In the left hand side I am having plus mu I into dNi. So I have same terms with the same sign, okay, in left hand side and right hand side. So we can cancel these two, right? Therefore, summation Ni into d mu I equal to Vdp minus SdT. Suppose if we keep temperature and pressure constant, right, at constant temperature and at constant pressure, if I keep temperature and pressure constant, then we get some summation Ni into d mu I equal to 0, and this is what we call as Gibbs-Duhem equation. Take down.